4 is going to be the start of our look at probability. You can see here the title of this chapter, our first section, is Sample Spaces and Probability. So as we get started here today, we're going to look through some definitions and terminology and what I would term to be simple probability or single event probability, and we'll move forward from there. So just running down through some of these definitions. Definition of probability is the measure of the likelihood that a certain outcome will occur in a given experiment. As a fraction, the probability of an event occurring is the number of favorable outcomes over the number of total possible outcomes. Kind of a generic definition there, but the bottom line is our probability is over the number of total possible outcomes. For example, if I have 52 card or a deck of cards, there are 52 cards in the deck of cards. So my total possible outcomes of drawing one out, there's 52 different cards I can draw out. If I want to draw out the King of Spades, there's only one King of Spades. Or if I want to draw out a king in general, there's 4 kings in there. But there's 52 total cards in there. So as a generic definition, probability is number of favorable over number of total possible outcomes. We talk about an experiment. That's our chance process. Outcome is the result of a single trial. So I draw a card out. That one card is my outcome. A sample space is a list of all the set of all possible outcomes of a probability experiment. So my deck of cards, my sample space, would be a listing of all 52 cards. Ace of Hearts, King of Hearts, Queen of Hearts, so forth for each of our suits. So all of our possible listings. With our sample space, sometimes a tree diagram helps us to sort that out and connect pieces together there. That happens especially when items happen in a sequential order. So for example, if I were to flip a coin 5 times, I want to find the probability of all 5 being heads. They happen in order. I could flip the coin the first time, it could be heads or tails. Second time, it could be heads or tails, and so forth. So we have items that happen in a sequential order, heads or tails, each time I flip that coin. So they happen one right after another. Quick description here. We classify our probability as one of 3 types: classical, empirical, or subjective. Classical is kind of what I just talked about up here with our deck of cards. Classical is where you can write down the sample space and use your sample space to come up with what's going to happen. So flipping a coin, a deck of cards, rolling 2 die, as in the game of craps, something that has a sample space that we can write down and read is classical in probability. Empirical probability is based on experience, such as polls or surveys or something like that. So not pools, how about polls? Polls, surveys, actual experience somewhere. Biggest or best example we can give out here is if we have a presidential election, the pollsters will start calling people to find out who they're going to vote for. So when they say so-and-so has 40% of the vote, that comes from actual talking to people and finding out who they're going to vote for. So 4 out of 10 people are saying they're going to vote for this certain candidate, whereas 3 others are going to vote for another candidate. So polls and surveys, those types of things make up empirical probability. Subjective, best example might be your betting lines in Vegas. If you, let's say, for example, maybe this year the Green Bay Packers are 10-1 odds to win the Super Bowl. Now, odds are different than probability, which we'll talk about later, but what that is doing is using information based off of the roster of the Green Bay Packers, their previous results, what they've done, and game scores and so forth, but there's still an element of guessing or hypothesizing as to the actual chances of that happening. Another great example, in my opinion anyway, would be a weather forecaster. They're going to use science, they're going to use some meteorology, they're going to use some maps, some other information, computer models, but ultimately when they say there's a 20% chance of rain, that 20% is somewhat of an educated guess. So it's a subjective probability Those are two pretty good description of subjective probability. Continuing down here, here's my fraction for the probability of the number of outcomes in our event, or the number of favorable outcomes in that event, over the number of total possible outcomes in that event. Probability must fall between 0 and 1. If something cannot occur, the probability is 0. So for it to snow in Hawaii, probability is 0. If a certain event is certain to occur, the probability is 1. The probability that the Earth rotates around the sun is 1, something like that. Sum of all probabilities of sample space does add up to be 1, so those are some definitions. Continuing on with a few more here, I believe. Go to the top. Complement of an event is a set of outcomes in that sample space that are not included in the event of E. So if I wanted to roll a single die and find the probability of rolling a 1, that probability would be 1/6. There's number 1 on the die, 6 total outcomes. So the complement of that is 1 minus 1/6, or there are 5 events that are not in there, 5 out of 6. So the complements add up to be a total of 1. We already talked about empirical and subjective probability. So let's get into some quick examples here. There are 8 red, 4 blue, and 6 white marbles in a drawer. If you draw 1 out without looking, find the probability of each of these next. Looks like 7 different problems. So looking here, 8, 4, and 6, there are 18 total marbles. That's going to be our denominator. Of those 18, we're going to find the probability of being red. 8 of those are red. So a quick little side note here, our probability as a fraction is always written in simplest form. Our probability can also be written as a decimal, or it can be written as a percentage. Now typically for the most part we're going to go this route, but it won't be too out of the ordinary to see them written as decimals as well. For right now we're going to work with the fractions, but just so you know that probability can be written as a fraction, a decimal, or as a percentage. The probability of a blue marble then, we're still out of 18. There are 4 blues that are in there, so our probability, I need to back up. I can't do math here for some reason. This was not 2/9, it was 4/9, which changes my decimal to be 0.444, or 44%. I don't know if I was peeking ahead or what I was doing there to get 2 out of 9, but my probability of 8/18 is 4/9, not 2/9, or not 2/9, because the probability of 4/18 is 2/9. Now we've cleared that up. Let's go on to white. We still have 18 to choose from. Of those, 6 are white. So 6 out of 18, and that simplifies to be 1/3. Going on, out of 18, of those 18, 0 are green, so there's no chance of pulling a green marble out of there because there are no green marbles. Probability of red or blue, notice there are 8 red and 4 blue out of our total of 18, or 12/18, which simplifies to be 2/3. Couple more real quick here, white or blue. There's still 18 to choose from. Of those, 4 are blue and 6 are white, so 10/18, which simplifies to be 5/9. And one more time, red, white, or blue. There are 4, 6, and 8 that are red, white, or blue, or 18 out of 18. We are sure to pull out a red, a white, or a blue marble because that's all that's in the bag. So there's our probabilities as a quick example of a single marble being drawn out, or a single event. Let's keep moving on here. Make a tree diagram for the gender of 3 children in a family. If we start over here, that first child can be a boy or a girl. If the first child was a boy, that second child can still be a boy or a girl. If the first child had been a girl, the second child could be either a boy or a girl. And we repeat the process. If the first child was a boy, the second child was a boy, the second child or the third child could still be a boy or a girl, and a boy or a girl for each of these 2 as well. If we follow our branches out, boy, 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 girl, and so on, we will list all the possible outcomes in a particular order. And you can see from this listing, this is called our sample space right here. These are all the possible outcomes of the different things that can happen in sequential order for the gender of 3 children in a family. So as we scroll down here a little bit, we have a couple questions to answer based off of that. It says, what is the probability that all 3 children are girls? Well, you can see right down here, this is the only place that we have all those being girls. So there's one outcome that's favorable, and 1, 2, 3, 4, 5, 6, 7, 8 total outcomes. So our probability is 1/8. Next question says, was it probably 2 boys and 1 girl? Well, there's 2 boys and a girl. There's 2 boys and a girl. There's 2 boys and a girl. So it looks like we have 3 of those. So our probability is 3/8. So there's using a tree diagram along with listing our sample space to come up with some probabilities. A couple more here with a deck of cards. I'm going to assume or hope that we all know there are 52 cards in a deck of cards. They're numbered 2 through ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace, and there's 4 suits. There's hearts, there's clubs, there's diamonds, and there's spades. So those of us that might not be familiar with a deck of cards, they're set up that way. There's 13 hearts, 13 clubs, 13 diamonds, 13 spades. Again, I'm hoping that most of us are familiar with that, so we're going to run through these questions fairly quickly. We're drawing 1 card out of here, so the probability of getting a jack, there are 4 jacks in a deck of cards, 1 heart, 1 club, 1 diamond, 1 spade, 52 total cards, and it was established earlier, our probability is always written in simplest form, so our probability is 1/13. Moving on, probably getting a 6 of clubs. We still have 52 total cards to choose from. In that deck, there is only 1 card that matches up as the 6 of clubs. There are 4 6s, but only 1 6 of clubs, so our probability here is 1 out of 52. Probably getting a 3 or a diamond. Here comes kind of a unique situation. Probably getting a 3. There are 4 3s in a deck of cards, so 4 out of 52. To that, we would add, there are 13 diamonds in a deck of cards. But we have a card that is a 3 of diamonds. So that 3 was added in here. It was also added in here, so we don't want to add it in twice. So we subtract this out, and we wind up with a total of 16 out of 52, which simplifies to be 4/13. We will talk more in depth about this little situation in the next section, something called the addition rule. But hopefully you get the idea of not adding the same card in twice. Okay, number 4, getting a heart or a diamond. There are 13 hearts. There are 13 diamonds. There's no overlap in those. So we have a total of 26 out of 52, or 1/2. And the probability of not getting a club of the cards in a deck of cards, 39 of those are not clubs. 13 are clubs, so 39 are not clubs. So 39 out of 52, or 3/4. Now, just as a side note, this kind of notation, not getting a club, is what's typically used with the idea of odds, but odds is something we'll talk about a little bit later on. Couple more problems here, and we should be good. 750 people were interviewed and asked to name the Vice President of the United States. 525 people answered correctly. Find the probability that the next person asked can correctly identify the Vice President. This, first of all, would be an example of empirical probability. I hope we can pick that up based on the fact that people were interviewed or surveyed and the results were recorded. But then our probability is the number of favorable, so 525 people answered correctly out of our total number surveyed in this case, which is 750. And if we simplify that down, we can simplify that down to 7/10. Just as a quick side note here, if we don't know how to use the fraction function on our calculator, I had 525 divided by 750. If I want to make that as simple as fraction as possible, I go to math. Right there at number 1 is a fraction. I can hit enter, and you can see that gives me a fraction of 7/10. So if we don't know how to simplify a fraction, using that graphing calculator might help us out a little bit there. Okay, having done that one should make the next one pretty simple. 18 freshmen and 23 sophomores in the class. Notice here there's 41 total in the class, 18 plus 23. If one student is chosen at random to answer a question, find the probability that the one chosen is a freshman. Well, of those 41 students, 41 total, 18 are freshmen, so 18 out of 41, that doesn't simplify, so that is our simplified answer there as far as the probability of a freshman answering the question. One last set here, we have a distribution that shows the number of days stayed at a hospital for maternity leave and how many actually stayed. So you can read through that: 15 for 3 days, 32 for 4, 56 for 5, 19 for 6, and 5 for 7. We're going to find probability, so I hope we've established by now for probability we need to know the number of total patients in this case, which we add these together as be 127. From here we simply answer the questions. Stayed exactly 5 days. Well, here 56 is exactly 5, so 56 out of our total 127. Less than 6 days, days that are less than 6 are 5, 4, and 3, so we're going to add those two together, and if we added those all together, it looks like we get 103 out of 127. That's 56 plus 32 plus 15. Stayed at most 4 days. At most 4 is 3 and 4, so 15 and 32 is 47 out of 107. Patient stayed at least 5 days. At least 5 would be 5, 6, and 7. So 56, 19, and 5. That would get us 80 out of 107. And that should wrap up our look at, our introduction anyway, to probability. Notice all those were a single event all the way through there, picking one person, picking one card, picking one marble, whatever the case might be. But that covers our first section, section 4.1, in our stats textbook.